Here we go. First of all, the inclined plane is a simple machine. A simple machine is something we use to give us a mechanical advantage. That is, it allows us to lift a really heavy thing without exerting a lot of force. Allows me to build pyramids and things like that. Simple machines. The simple machines, and you may have heard of them, are like the inclined plane, the wedge, the lever, the wheel and axle, the pulley, and the screw. So there's 6 simple machines. One of them is the inclined plane. Let me just give you a really quick, shot of the inclined plane. Let's say you've got this 50-gallon drum, and you need to lift this 50-gallon drum onto this landing here. It's a 50-gallon drum filled with water. Well, a 50-gallon drum filled with water weighs about 400 pounds. There's no way you're going to be able to lift that thing up 6 or 7 feet onto that landing. But what you could do is build a ramp that goes to the landing. And now, here you are, and you're going to roll that thing up the ramp. And you will not have to exert 400 pounds. You'll have to exert some force, depending on how steep the ramp is, but you're not going to have to exert 400 pounds. And so you roll that thing up the ramp, and then you get on the landing, and you feel very proud of yourself. And that's an inclined plane. You have to pay for this mechanical advantage, and what you have to pay is exerting a force over a longer distance. Here, if I wanted to deadlift this barrel onto here, I only have to move the barrel, 7 feet, and it's on there. If I want to roll the barrel up this ramp, I might have to roll it up a 25 or 30-foot ramp. So I'm having to exert this smaller force over a greater distance, and that's okay. You're willing to pay that price. So that's the purpose of an inclined plane. I need to introduce you to being able to do physics on inclined planes. So here we go. Inclined plane. Suppose I have an inclined plane. This plane is inclined at a 25-degree angle. It has a mass M on it. A mass of mass M. And suppose it's frictionless. The coefficient of static friction equals the coefficient of kinetic friction, which equals 0. It is frictionless. There's a process I'm going to want you to follow when you do an inclined plane problem. And the process goes like this. First of all, your x and y axes are no longer going to be horizontal and vertical. No siree. Your x and y axes will now be parallel and perpendicular to the plane. If you want, you can draw them. Here, I'm going to do that. Here's my x-axis. Here's my y-axis. My x and y axes are now parallel and perpendicular to the plane, not horizontal and vertical. Next, let's go ahead and draw a free body diagram. There's 2 forces acting on this mass. One force is gravity, which comes straight down. And the other force is normal force, which acts perpendicular to the surfaces in contact. This mass is going to slide down the ramp. You know that to be true. Is there a third force? Do I need to draw a third force pulling the mass down the ramp? Well, the answer is no. Correct? I don't have a string attached to the mass that I'm yanking on. I don't have somebody standing behind the mass shoving it. There is no force pulling it down the ramp, save for one, and we're going to see that momentarily. Tell me, whenever a force is at a weird angle, you know that we have to get the x and y components of the force. Which of these 2 forces is at the weird angle, requiring me to get x and y components?
The weight.
How many people say the normal force? How many people say mg? Well, good for you guys. Why mg? Gavin, why'd you say mg?
Because it's not on the x-axis.
Yeah, because mg is not on the x or y axis. Sure, in vertical and horizontal land, I wouldn't have to get the x and y components of mg, but I'm not in vertical and horizontal land. I'm in inclined plane land. And in inclined plane land, the x-axis is parallel to the plane, and the y-axis is perpendicular to the plane. So your x and y components are going to have to be of mg. And let me show you how I want you to draw it. I want you to draw your y component to be on an opposite ray from the normal force. So you see how the normal force is going like this? I drew my y component to be opposite, vector to the normal force. And then your x component, should my x component be completely horizontal? That is this correct? Would that be a correct representation of the x component of mg? Yeah, no way. What's that x component going to have to be? What attribute must it have? Yes, no, I'll go and say it.
It's got to be at the same angle that the x-axis is.
Thank you. It's got to be at the same angle as the x-axis. It's got to be parallel to the x-axis. So do your best to represent these forces as being perpendicular and parallel to the ramp. Now let's consider angles. This is a right angle right there. This is a 25-degree angle. So how many degrees does that make this angle right there? Yeah, if you're thinking 55 or 75, your heart's in the right place, but it's actually 65. You guys okay with that? So this is a 65-degree angle. And now look at the y-axis relative to the plane itself. They're perpendicular, correct? So since that's 65, that angle is going to be what? They got to add up to 90. You guys thinking 25? Okay, good. 25. So is that going to be true? Is this angle always going to be the same as that angle? Yep, it sure is. It'll always be. This little angle will always be the same as that angle because they're both complementary to the same angle, right? This angle and that angle have to add up to 90. This angle and that angle have to add up to 90. So, complements of congruent angles, or complements of the same angle, or congruent angles are congruent. You learn that in geometry. Now it is time for us to get an expression for the x and y components of mg. And we're going to do the same thing like we did on problem number 60 that was due yesterday. That one problem where you had a sign being held up by two tensions at weird different angles. And the way you had to deal with it was actually to call this tension T1 cosine theta, and this tension was T1 sine theta, and this was T2 cosine theta, T2 sine theta. Remember that problem? Well, you're going to have to do the same thing here. Consider the y component of mg, the y component of mg. Do you see that the y component of mg over mg is going to be equal to the cosine of this angle? The cosine of the angle is this guy over mg. And so mg cosine of 25 degrees equals the y component of mg. So this guy here is mg cosine of 25 degrees. And you tell me, what's this guy going to be? Yeah, thank you very much, Yvonne. Mg sine of 25 degrees. So remember when I asked you earlier, do I need to draw a force pulling this mass down? The answer is no. I mean, you tell me, what's the force pulling that mass down the ramp? Someone please tell me or raise your hand. What's that? No, normal force is perpendicular to its motion down the ramp, so normal force isn't going to have any bearing. Yes, Gavin?
It's on weights point of time?
Okay, but tell me more. Mg isn't what's pulling it down the ramp. Which, yes, Fatima? Thank you, it's the x component of weight. It's the mg sine 25. That's what's pulling it down the ramp, right? That's the force that's pulling it down the ramp. You don't have to draw me a force showing it's pulling it down the ramp. There it is, mg sine 25. Now we're ready to do some of the forces in the x direction equals max, some of the forces in the y direction equals may. But I just want to talk about the keys to doing these inclined plane problems. First of all, you need to draw your x and y axes parallel and perpendicular to the ramp. Draw x and y axes parallel and perpendicular to the ramp, to the inclined plane. And you don't have to draw it every time. You can get to the point where you just picture it in your head, but you still need to know that the x and y axes are parallel and perpendicular to the ramp. Step 2, when you do mg, draw your y component of mg as being an opposite vector to normal force. Draw the y component of mg as an opposite vector to the normal force. You'll just find that it gives you a better look for your free body diagram. And of course, you're going to discover that the perpendicular component of weight is always mg cosine 25. The parallel component of weight is always mg sine of 25 degrees. Cosine 25 degrees and then sine of 25 degrees. All right, well, let's go ahead and answer the question. Oh, I never got around to asking the question, did I? Get acceleration down the ramp. That's the question. Okay, let's go for it. Sum of the forces in the y direction equals NAY. I got normal force minus mg cosine of 25 degrees equals 0. I'm not accelerating in the y direction. The mass is not hopping off to the stars. The mass is burrowing into the plane. So I get normal force equals mg cosine of 25 degrees. Did I need to know what the normal force was? Or maybe ask it a different way. Under what circumstances would I need to know what the normal force was? What's that? Okay, if it's moving, but under what circumstances? Yeah, Fatima?
There's friction.
Yeah, if there's friction. If there's friction, I need to know what the normal force is, but not here. Is that what you said, Chris? But I misheard.
If it's moving, wouldn't there be like friction? Like if there's kinetic friction.
You'd think, but I'm in this pretend world of example number 1. There's no kinetic friction. But yeah, you're right. Okay, so in real life, yeah, there's friction. Okay, so let's go ahead and do this thing. The sum of the forces in the x direction equals max. I only got one force acting in the x direction. Mg sine of 25 degrees equals max. By the way, can someone tell me, why did I never get around to telling you what the mass of that object is? Because they cancel. If you put me and Noel on the same ramp, we'd slide down at the same rate. The fact that I'm significantly more massive than she is irrelevant. And so I got g sine 25, which ends up being approximately 4.1 meters per second squared. You guys okay with that? G sine 25, that was my acceleration. Let me just ask you generally, if I've got an inclined plane that's frictionless, okay, and the angle is theta, what's the acceleration of this mass down the plane just generally, if the angle was just any old angle, theta, and it was frictionless? You guys thinking g sine theta? Right, doesn't matter that it was 25, this could have been any angle. G sine theta. Okay. Well, hey, that was fun. Well, let's go ahead and deal with the situation where there is friction. Redo example number 1, only now mu sub k equals 0.2. I'd like everyone to please make a drawing, do a free body diagram, and then do some of the forces. I'll give you a minute or two, and then I'll intervene. But I want to see if you can do a proper free body diagram. And I want you to do the free body diagram on the ramp. Don't put it off to the side. This is a situation where I want the free body diagram on the ramp. I want to see mg on the ramp, etc. Please do your free body diagram on the ramp. I'm gonna walk around and just make sure you're making good free body diagrams. What the heck is that? It's got a point in the y direction along that dotted line you said. Your normal force was off at some weird angle. Your normal force has to be perpendicular to the ramp. Which means,
Oh, I drew it weird here, but I drew it right now.
Eugenia, I don't know why either. It's a mystery.
You don't know?
Where's your friction force?
Oh.
Oh, by the way, this guy is sliding down the ramp. So because he's sliding down the ramp, what's the direction of friction force going to be? Are they going to up the ramp? Hopefully. So draw your friction force up the ramp because he's sliding down the ramp. It's a different story if he was sliding up the ramp. You're so okay. So you think that's perpendicular? That line is perpendicular to that line? You guys are crazy, man. What's that? Nothing. Yeah, the only force bringing it down the ramp is this component of gravity, and make sure you make that component parallel, which is almost kind of the same. Very nice. That's very, very nice.
Huh?
Because you're getting, now give me your mg and your friction force and
Like
you're
some
good.
friction.
How do I
Good
spell?
for you.
So,
Oh,
See, I'll do that big.
going down.
just to like.
Okay, yeah, that's beautiful.
I try.
Okay, get that off of there. There's no
Parallel to the
force
ramp.
taking it down the ramp. The only force taking it down the ramp is the x component of mg, which you haven't drawn yet. That's beautiful, perfect. Now go ahead and do some of the forces in the y direction. Get what the normal force is, then some of the forces in the x direction. And you'll be so happy. You'll be pleased. Pleased as punch. One thing I want to remind you is when you do the x component of gravity, have it be parallel to the ramp. Like I'm not quite sure what's going on there. Okay, that's beautiful. Okay. Oops. Sorry about that. Pooja, this component of mg should be parallel to the ramp. You drew it at some weird angle. It should be like that's mg. You should be looking at something like this. Okay, so that this guy is parallel to the ramp. That's your x component of mg. You guys are just zipping along. Where's your free body diagram? Oh, there it is. Never mind. You're good.
Oh my goodness.
Good for you. I'm in the smart part of the class, obviously. This side here. See what's got. Cool. Yeah, that's all great. You're ready to do your thing. Yeah, great. Make sure you have arrows on those components pointing down and pointing down the ramp.
Ours is just like, is it supposing as it should?
Don't forget your normal force. Yeah, you got a normal force up. Ooh, Well, hey, looking good. Hey there, Noel. Good to see you. Yeah, oh, you're so smart. Don't ever change. No matter what, even if every single person in your life tells you to change, don't change.
Yeah, would you?
3.96 meters per second squared.
Which arrow? Well, the friction is only pointing up the ramp, so what you had crossed out was actually a correct friction. Alright. Where's your friction? The friction force pointing up the ramp.
That's right.
So here's your friction force up the ramp. The normal force perpendicular to the ramp.
I got 2.7. That's what I got.
2.37.
Well, I better.
Wait, Stanley, what did you get wrong?
You better.
I hope you guys did all right.
I just figured it's down because
I usually figure it's me.
Okay, shoot, I'm kind of running out of time a little bit.
Hold on.
Here. Hopefully you got normal force perpendicular to the ramp. Hopefully you got kinetic friction force parallel to the ramp. Hopefully you got your y and x components of mg. The x component of mg is mg sine 25 degrees. The y component is mg cosine of 25 degrees, because this angle will always be 25 degrees. And there's my free body diagram. Now, one thing I forgot to mention in the previous problem is I have to define what direction is positive, and I tend to define that direction as positive and down the ramp as positive. So, hey, let's go ahead and find our coefficient, or rather, find our acceleration. Sum of the forces in the y direction equals may. Normal force minus mg cosine of 25 degrees equals 0. And as happens virtually every time, my normal force is mg cosine of 25 degrees. Yay. Now I'm ready to consider the x direction. Sum of the forces in the x direction equals max. I've got two forces in the x direction, mg sine 25 bringing it down the ramp, and kinetic friction force resisting that motion. And this equals max. My coefficient of my kinetic friction is mu sub kf sub n. You're always going to make that substitution for friction, mu sub kf sub n or mu sub s f sub n. And f sub n, what is this, 0.2? F sub n is mg cosine theta, mg cosine 25 degrees. Do you see again why I didn't get around to telling you what the mass of the object is? Again, me and Noel, we would slide down at the same rate. And so now you do the math and you get 2.4 meters per second squared. Any question or problem with this process? Then I need to give you a couple of problems that concern themselves with static friction. Here. One easy, hard, and one easy. Well, no, both of them are easy. Okay. Imagine this. I've got a guy with a board, and the board has a book on it, and he lifts the board until the book just starts to slide. Lift board until book just starts to slide. And he finds that that angle is a 30-degree angle. It just starts to slide when he lifts the board to a 30-degree angle. we're going to find the coefficient of static friction between the book and the board. Find the coefficient of static friction if it just starts to slide at 30 degrees. Well, what do you suppose I'm going to do first? If you're thinking 3-body diagram, you win. So here we go. I've got mg, I've got my normal force perpendicular to the ramp, and I've got my static friction force that's going up the ramp. Static friction force is going up the ramp because the net force on the book is down the ramp, or at least until the friction force kicks in. I'm going to get the x and y components of mg. This is mg sine of 30 degrees. And this is mg cosine 30 degrees. I do sum of the forces in the y direction equals MAY. And just as the other two times, my normal force ends up being mg cosine times the angle. And now let's go ahead and do the x direction. Sum of the forces in the x direction equals MAX. So I've got mg sine of 30 degrees minus f sub s equals, if something is just starting to slide, that is, it breaks the bonds, but it hasn't started moving yet, what do we in this class designate its acceleration as?
0.
Yeah, good for you guys, 0. And my static friction force is, is going to be mu sub s times f sub n. Do you notice now not only do the m's cancel, but the g's cancel? And I end up with mu sub s equals the sine of 30 degrees over the cosine of 30 degrees. That is, mu sub s ends up equaling the tangent of 30 degrees, which is about 0.58. But does the angle matter? What I mean is this. Suppose this dude is just lifting the board and the book starts to slide at any angle theta. What's the coefficient of static friction going to be no matter what the angle theta is? Good, tangent theta, right? So I just want you to be aware of that. I'd now like to give you an incredibly easy problem that's deceptive. Like you think it's hard, you don't know what to do, but it turns out to be incredibly easy. Here it comes. Example number 3 or 4, I don't know what it is now. A 5 kilogram box is at rest on a 10-degree ramp where the I'll just do that. 5 kilogram box at rest on a 10-degree ramp. Find the static friction force on that box. Yes.
Do you want it?
What's this?
You want cheap?
Oh, sure. Thank you. I love these things. I should tell the video. Leilani just gave me one of these. I love these. But do I look funny?
No, because it was zoomed around on your face.
Okay. Hey guys, what do you suppose I should do first?
free body.
Yeah, free body diagram, right? Because I'm a little faked out here. I mean, I know under normal circumstances, if I'm sliding a box across the floor and it won't move, then whatever force I'm exerting, that's the static friction force, right? So I'd be going, well, mg mu sub s. But what about when something's on a ramp? This is on a 10-degree ramp, okay? 10-degree ramp. Here's my box. Here's my normal force. Here's my gravity. Here's my static friction force. As always, normal force is going to be mg cosine, in this case, 10 degrees. We got this and this. This is mg sine of 10 degrees, right? Thing's not moving. So you just tell me visually, what's my static friction force equal to? Yes, Cole?
Is it tan of 10 degrees?
No, not tan. Like, look, I got two forces in the x direction. Static friction force that way, mg sine 10 degrees that way, and it's not moving. So go ahead, DeAndre.
Mg sine of 10?
Yeah, mg sine of 10, right? It's that simple. My static friction force is mg sine of 10. I mean, I can do some of the forces equals ma, but I just want you to see visually that's what it is. That's my friction force, mg sine of 10. How do I know? Because I'm looking at it, you know? The mg sine 10 and the f sub s, it's in equilibrium. Those two forces are equal and opposite. Is that the maximum static friction force, possible here? No, I mean, it could have a lot more friction. For all I know, you can lift it to a 40-degree angle. But right here at a 10-degree angle, your static friction force is equal to that. Okay, hey, there's one more type of problem I need to make sure you can do, and that's this. What if I told you that the angle is 40 degrees and the acceleration down the ramp is 2.5 meters per second squared? Find the coefficient of kinetic friction. So I've got a 40-degree angle. I've got this mass. And it's going to accelerate down the ramp at 2.5. What would you recommend I do? Well, I hate to be a broken record, but free body diagram. You got mg, you got normal force, and you got kinetic friction force. You got mg cosine of 40 degrees, and you got mg sine of 40 degrees. You do the sum of the forces in the y direction equals may, but it ends up just normal force equaling mg cosine of 40 degrees, like always. And now finally, we turn our attention to the x direction. I'm going to define that way as positive and that way as positive. So I got sum of the forces in the x direction equals max. I got mg sine of 40 degrees minus mu sub k mg cosine of 40 degrees. That's my friction force, kinetic friction force, equals m times 2.5. And at this point, I'll say etc. I mean, there it is. Now you can cancel the m's and you can solve for mu sub k. Do your algebra and solve for mu sub k. So these problems all look the same. As long as you draw a good free body diagram and do some of the forces in the y direction, some of the forces in the x direction, you should be fine. And tonight's homework, like a lot of them, are just like this. They're just drawing free body diagrams and making conclusions. Any questions or issues on any of this? Alrighty, then we're done.